And uh, today let's see how to write kernels in Python. So as kernels are written, so these kernels are mostly written for GPUs. So Python is useful for writing GPU kernels. So why do we need kernels? So kernels enable us to optimize the GPU utilization, and they standardize the how how can we use both GPU memory and utilization in the best way possible. So the major problem, as we know, like, so between a CPU and a GPU, GPU is built for handling more tasks, wide range of tasks, whereas GPU is specifically built for running same task multiple times. So the whole point of having a GPU is executing a task which is repeatable and which can be broken down. So let's start with a simple example. So here we have so this is like the few Triton examples that we have. So let's start with the most like simplest thing that we can have, the vector addition. So here we have a two vectors, x and y. We want to add both the vectors. So in a CPU, how we will do is we'll use a for loop and we'll loop over each index and we'll try to add them. And here, the only benefit from a CPU side we are getting is that we'll be loading a cache line. So in cache line, we'll be having like few of the elements cached. So they will be in L1 memory. So we can make use of that. But essentially, if you see the problem, there is no dependency on like the summation. So you can do the zeroth index summation of x and y, and you can do the some nth index of x and y. Both are independent. So actually, we can like completely parallelize this process, and that's what here a GPU will do. So in this example, is the like simplest example that we can show with the GPU. So here we launch any number of programs. So each program's task is to compute the specific element wise summation of the x and y. So, so let's say the uh, x is a size 5 array and y is a size 5 array. So we'll be launching 5 programs which will compute everything parallelly, like x0 plus x1 and x1 plus y1 will be computed parallelly and we'll be getting result at once. So let's just look at how to write this kernel. Uh, so basically, we just have to import the Triton library and the Triton language package. So before any Python program, we to mention it's a Triton kernel, we need to add Triton.jit. Rest of it is like Python, but the syntax is very closer to how we will write a uh, algorithm. So here we will launch a 1D grid. Uh, so since the x and y are in one D, we'll launch a 1D grid, and will like the starting point is the uh, like how like starting point is the like the first kernel and how many blocks we have. Like we here we have like the size of x pointer blocks, and that will be size of blocks. So offset offset is to uh, to make sure that we are not reading anything out of memory. So we have block start here. So but block size might be less than or greater than the size of x pointer. If we set it like if we take a block size which is not equal to size of x pointer, the operations that we'll be doing with the uh, x and y vectors will lead to a out of memory read. So to make sure that we need to have the offset, So for that, we are taking this mask, and this is basically so uh, the number of programs that we are launching or the number of pointers that we are handling should always be less than the number of elements that we are computing. So this is the mask. So after this, we load both the vectors into the GPU memory. So Python.load will load both the both the x and y. So here we're adding the offset and mask. So anything uh, above the x pointers range, if we hit the mask condition, we won't be touching that memory. And once we load the x and y, we can directly compute the output, which is x plus y, and store it in store it in the output memory address. So this is like a very simple kernel. So here we can clearly see the how how to like parallelize the process. So with the CPU, it's sequential essentially. We have the cache line reads, but they're not enough. So let's look at another example. So it's a fused kernel. So, so kernel fusion is a very important technique in writing GPU kernel. So, why kernel fusion involves is uh, so we want to we want to like completely minimize the IO we have, and once we do a IO operation, we want to use the data as much as possible, and we don't want to do any unnecessary IOs. The reason being, like when we are doing IO, the GPU is installed, so the GPU is waiting for some memory to load and continue the task. So which is not a ideal scenario. So we shouldn't be like wasting our time on IO. So to do that, we should write kernels which are fused and utilize very less IO and try to do as much as possible inside inside the fusion. So this is the fusion for softmax. So softmax on a 2D array. So softmax on a 2D array per row, how it will look like is like each row will have we need to take uh, like the denominator will be a summation of the exponents of the row values. So each element will get for a ith element in jth row, it's eij divided by summation of e ei. So that's the each element wise. So what if we don't fuse the kernel? So if we don't fuse the kernel, if we go straight forward and implement the softmax layer wise, so first what we'll do, we will like find the max out of each row. uh, and then the next step is to like the next step is to oh sorry we'll like compute the summation of the row wise, and then we go ahead and do the element wise calculation of the softmax. But here if you see, each time when the each time when you ask Python to write something, it will load a different kernel, so which kind of loads different IO. So every time we are doing the M into N rates. So to save the time, we need to like completely fuse the kernel. So previously also we did fuse the kernel. So we did a fusion on elements. So we launched 5 programs, and each program is independent and everything is fused. So now here the fusion is not so straightforward and not so row wise. So here the fusion is on the max compute unit that we have. So each GPU will have some streaming process, and each streaming process will have its own thread graphs. So based on that, we need to compute like what is the max allowed computations that we can go ahead, and we will divide this entire X matrix, like let's say we have like 4,000 rows. We will divide this 4,000 rows into blocks of computable things. So first one to, let's say we have a total of 50 execution units in a GPU. The first 1 to 50 tasks will be taken by each of the computer. Then 51 to 100 will be taken again by the 1 to. So essentially the computer unit 1 in a GPU will be taking 1, 0, 50, 100, 150, so on. So that is what here we're doing. So we are having this row pointer. So we start with row start and the program ID. So it will runs the program. So the row step will, like, this number of programs is the, like, the max compute units we have. So, and this uh, is is in which step are we in right now. So for a, let's say for a uh, compute unit 1, it is taking care of 0, 50, 100 and 150, and in this stage which step we are in. So if you see, we loop over the row index and this the like uh, take the elements from row start to uh, number of rows, and the, like, the jump is the row step. So row step is basically the programs that we are allowing. So this is 0, this is the max that we have. Let's say it's 1,000. 0,000 row step is 50 because we have 50 execution units. So uh, we so first 0 to 50 we will get. Uh, then we'll calculate the row starting pointer. Uh, so why row starting pointer is needed is like so this will, like, since the data is stored sequentially in a GPU from a memory point of view. So this will the like this will give the starting pointer, and if we stride till the column values, we'll get all the values in the given row. So this is again the same offset map that we have to make sure that we don't go to a OM, and then we load the row. Once we load the row, do the we do uh, this softmax calculation, and we update the output. We update the output pointer of the current row in the, like, resulting softmax output layer with the current softmax output that we got. So in this way, we are loading only the needed ones, and and here we can even this, since we have the num stages already calculated, since we know that the uh, the execution unit 1 is going to take care of 0, 50 and 100, we can uh, preload the data on flight, like similar to how we do it in the CPU instruction sets and all. So yeah, these are the, like, two examples that we'll talked about. Have written a custom kernel as well. So maybe we'll discuss it in is this is the in upcoming videos. But thank you.